Picture this: 7 spacecraft, all orbiting Mars, all positioned perfectly on October 3rd, 2025. Their mission? To capture the sharpest images ever taken of an object that doesn't belong to our solar system. An interstellar visitor that traveled through the darkness between stars for billions of years, only to arrive here, now, at this exact moment in human history. NASA's Mars Reconnaissance Orbiter alone promised resolution 20 times better than the Hubble Space Telescope could manage. This should have been the day we finally understood what this mysterious object really is. Instead, it became the day everything went silent. 2 days before this historic event, something happened. The United States government shut down. NASA's website went dark. And when images finally appeared from the European Space Agency 4 days later, all we got was one fuzzy white dot. One image. From 7 spacecraft. Where are the rest of the photographs? What did those cameras actually capture when this visitor passed within 30 million kilometers of Mars? And why does it feel like someone pulled the curtain closed right as the most important scene was about to unfold? But before we dive deeper into what might be one of the strangest mysteries in modern astronomy, I need you to do something for me. Hit that subscribe button right now. This channel brings you the most fascinating stories at the intersection of science and mystery, and you don't want to miss what's coming. And please, leave a like on this video. It helps more people discover these incredible stories. Understanding what you're about to hear matters more than you might think. This isn't just about one object passing through our solar system. It's about how we respond when something challenges everything we thought we knew. So stay focused, stay curious, and let's unravel this together. Now, let me take you back to where this story really begins. July 1st, 2025. The Atlas telescope in Chile picks up something unusual. Within hours, astronomers are pulling archived images from observatories around the world. This object had actually been photographed going back to June 14th, but nobody had noticed it yet. When they finally plot its trajectory, one thing becomes immediately clear. This thing isn't orbiting our sun. It's passing through. A visitor from another star system. They name it 3I/Atlas. The third interstellar object ever confirmed visiting our solar system. You might remember the first one, Oumuamua, which caused quite a stir back in 2017. Then came Borisov in 2019. But 3I/Atlas arrived with something the others didn't have. A trajectory that seemed almost impossibly perfect. Think about our solar system for a moment. All the planets orbit in roughly the same flat plane, like marbles rolling around on a table. Most objects coming from deep space approach from random angles, above or below that plane. Oumuamua came in at a steep angle. Borisov too. But 3I/Atlas? It arrived at just 5 degrees from perfectly aligned with our planetary plane. Avi Loeb, the chair of Harvard's astronomy department, ran the numbers. The probability of an interstellar object arriving within 5 degrees of our ecliptic plane just by random chance? About 1 in 500. Now add this detail. This object's trajectory would bring it close to Mars, then Venus, then toward Jupiter. The combined probability of all of that happening purely by accident? 5 in 100,000. You're starting to see why some scientists raise their eyebrows. Natural comets don't typically arrive gift-wrapped with optimal viewing angles. But the trajectory was just the beginning of the strangeness. As summer progressed, more telescopes turned toward 3I/Atlas. The Hubble Space Telescope captured images in late July when the object sat 277 million miles from Earth. What those images showed challenged every expectation. Most comets display a bright nucleus with a tail streaming behind them, pushed away from the sun by solar radiation. It's the classic image we all recognize. But 3I/Atlas had something different. The glow extended forward, toward the sun, not away from it, like it was pushing through something rather than being pushed. Behind it, where you'd expect a prominent tail, there was almost nothing. Scientists at UCLA processed those Hubble images carefully. They measured the forward glow extending thousands of kilometers. The bright region was roughly 10 times longer than it was wide, creating an elongated teardrop shape pointing sunward. Natural outgassing from a comet nucleus doesn't usually create patterns like that. Solar radiation should be actively pushing material backward, not forward. Then came the chemical analysis, and things got even stranger. The James Webb Space Telescope observed 3I/Atlas on August 6 using its infrared spectrograph. Webb can break down the chemical composition of objects by analyzing specific wavelengths of light. What it found was deeply unusual. The gas cloud surrounding this visitor was dominated by carbon dioxide, 87%. Carbon monoxide made up about 9%. And water, the primary component of almost every comet we've ever studied from our own solar system, comprised only 4%. Think about that. Every comet humanity has observed from our solar system is typically water-rich. They're icy bodies that formed in the cold outer regions around our sun. When they warm up, water ice turns to vapor, creating those brilliant tails. But 3I/Atlas seemed built differently. 87% carbon dioxide is almost unheard of. Only one other comet in all our records shows anything similar. This wasn't just unusual. It was anomalous. Then the Sphere-X Space Observatory studied the object between August 7th and 15th. Sphere-X operates in the infrared, measuring how much sunlight reflects off objects to estimate their size. The data suggested something that made astronomers pause and recalculate. Based on the infrared light bouncing off 3I/Atlas, the nucleus could be as large as 46 kilometers in diameter. 46 kilometers. For context, Borisov, the previous interstellar comet, had a nucleus estimated at around 1 kilometer. If the Sphere-X measurements were accurate, 3I/Atlas could be 1,000,000 times more massive than Borisov. 1,000,000 times. Avi Loeb calculated what this size discrepancy might mean. At solid density, if 3I/Atlas really is that large, we're talking about a minimum mass of 33 billion tons. But here's what troubled him most. If interstellar objects follow a normal size distribution, we should have detected hundreds or thousands of smaller objects before ever encountering something this massive. The Atlas telescope system has been scanning the sky for a decade. 3 interstellar visitors in all that time, and suddenly the third one is 1,000,000 times bigger than the second? The statistics don't support that kind of distribution. Unless the size estimates are wrong. Unless what Sphere-X detected wasn't the solid nucleus itself, but an enormous cloud of dust surrounding a much smaller core. But that explanation creates its own problems. If 3I/Atlas has a dense dust cloud large enough to reflect that much infrared light, where's the tail? Solar radiation should push all that dust backward, creating a spectacular tail visible in every image. Instead, telescopes saw mostly forward scatter and minimal trailing material. Throughout August and September, more observatories captured additional data. The Very Large Telescope in Chile detected cyanide molecules being released from the object. But what caught attention was how rapidly that production rate increased as the comet approached the sun. The emissions scaled with a power of -9.4. Most comets show production rates that scale with powers between -2 and -4. 9.4 is extraordinarily steep, almost impossible. The Very Large Telescope data revealed something else that didn't make sense. They detected nickel in the gas plume around 3I/Atlas, but no iron. In nature, nickel and iron almost always appear together. They're both produced in supernova explosions and get incorporated into forming solar systems in relatively fixed ratios. Finding nickel without iron is like finding smoke without fire. It happens in very specific industrial processes where nickel alloys are manufactured, but in natural space objects, it's deeply anomalous. Then in early September, amateur astrophotographers captured images of 3I/Atlas during a total lunar eclipse. Their photograph showed something unexpected. The comet, which had appeared reddish in all previous observations, now glowed green. Green comets aren't uncommon. The color typically comes from diatomic carbon molecules that fluoresce green under solar ultraviolet light. But here's the problem. Earlier observations found that 3I/Atlas showed extreme carbon chain depletion. The comet had significantly lower levels of these carbon molecules than any other comet on record. If 3I/Atlas lacks diatomic carbon, what's causing the green glow? The combination of high carbon dioxide, low water, depleted carbon chains, abundant cyanide, nickel without iron, and now a green glow that shouldn't exist based on its molecular inventory painted a picture of an object that didn't fit any template scientists had for natural comets. By late September, 3I/Atlas had moved close enough to the Sun that observing it from Earth became difficult. The geometry placed it near the Sun's position in our sky, drowning it in solar glare. From Earth-based telescopes, the visitor effectively vanished into brightness. This is where Mars became critical. Mars sits much farther from Earth, but in early October 2025, spacecraft around the red planet had a much better viewing angle. As Earth lost its line of sight, Mars gained one. 7 orbiters circled Mars. NASA's Mars Reconnaissance Orbiter carried the HiRISE camera, arguably the most powerful camera ever sent to another planet. HiRISE can resolve features down to 30 centimeters from its orbital altitude. Pointed at 3I/Atlas during closest approach, its resolution would be 20 times better than what Hubble achieved. NASA's MAVEN spacecraft carried ultraviolet spectrographs that could analyze gas emissions. The European Space Agency's Mars Express and ExoMars orbiters featured cameras and spectrometers for compositional analysis. China's Tianwen-1 contributed imaging capabilities. The UAE's HOPE orbiter brought multiple instruments. 7 spacecraft, multiple cameras, multiple spectrometers, all positioned perfectly to capture data during 3I/Atlas's closest approach to Mars on October 3rd. Astronomers worldwide anticipated this would provide the clearest look yet at the interstellar visitor. The pieces were in place. The timing was perfect. The instruments were ready. And then, 2 days before the event, the United States federal government shut down. When a government shutdown occurs, NASA typically furloughs around 80% of its workforce. Public affairs offices close. Social media goes quiet. The main website displays a message about lapsed funding. But mission-critical operations continue. The Mars orbiters don't stop functioning. Data still flows from spacecraft to ground stations, gets recorded, gets stored. What changes is the pipeline for public release. NASA's raw image archives for Mars missions normally update continuously. During operations, raw images appear within hours of being taken. The system is largely automated, but processing those raw images into calibrated, analyzed, publication-ready formats requires human expertise. On October 1st, 2025, that human expertise got furloughed. Over 15,000 NASA employees received notices. The timing meant that when 3I/Atlas made its closest approach to Mars on October 3rd, the people who would normally process and release spacecraft imagery were at home, prohibited from performing official duties. The European Space Agency, not subject to United States funding politics, continued operations normally. ESA's spacecraft both observed 3I/Atlas as planned. On October 7th, for days after the Mars flyby, ESA released images publicly. The scientific community and space enthusiasts who had been waiting with anticipation finally had something to examine. What they saw was a fuzzy white dot moving across a starfield. The images confirmed 3I/Atlas existed, confirmed it had passed Mars as predicted, but revealed little about its structure or composition. The instrument that captured these images was designed to photograph the bright surface of Mars from close range, not dim objects 30 million kilometers distant. The comet appeared roughly 10,000 to 100,000 times fainter than typical targets. That it detected anything at all was impressive, but the resolution was limited. Meanwhile, speculation about NASA's images intensified. 7 spacecraft had been in position. The Mars Reconnaissance Orbiter's high-rise camera should have captured extraordinarily detailed views. Yet nothing appeared in public archives. The automated raw image feeds from the Perseverance rover continued updating, showing usual surface geology, but no processed images of 3I/Atlas materialized. On October 4th, just one day after the flyby, something appeared in the Perseverance raw image archive that caught attention. The navigation camera had captured an image showing an elongated streak of light against the dark sky. The timestamp coincided with when 3I/Atlas would have been visible from Mars. Amateur astronomers immediately began downloading and analyzing the image. Some stacked multiple frames together to boost faint details. They identified what appeared to be a smudge of light close to where orbital calculations predicted 3I/Atlas should appear. But the morphology of that streak raised questions. The object appeared roughly 4 times longer than it was wide, creating a cylindrical appearance. Social media erupted with comparisons to Oumuamua, which had also displayed an elongated shape. Was 3I/Atlas actually cylindrical, or was something else creating that appearance? Analysis suggested the navigation camera image was likely a composite of hundreds of individual frames taken over approximately 10 minutes. During that time, 3I/Atlas would have been moving across the Martian sky. If frames were stacked together without accounting for motion, they would create a streak. The length of that streak would depend on integration time, not on actual physical dimensions. Think of photographing a car driving down a highway at night with a long exposure. The car itself might be compact, but in your photo, it appears as a long streak of light. The streak doesn't represent the car's actual shape, just its motion during exposure. The same principle likely applied here. The cylindrical appearance probably resulted from motion blur, not from 3I/Atlas being physically elongated. Still, NASA hadn't confirmed whether the navigation camera images even showed 3I/Atlas. The agency remained silent. Given the government shutdown and furloughed public affairs staff, perhaps that silence was understandable. But lack of clarity left room for speculation to flourish. Then came unverified reports circulating through space enthusiast communities that NASA had provided preliminary briefings to select media outlets on October 4th, just 24 hours after the flyby. These briefings allegedly characterized 3I/Atlas as an ordinary comet without addressing any anomalous features that had puzzled astronomers. No supporting technical reports accompanied these briefings. No images were released, just verbal assurances that everything was normal. Some researchers who study government secrecy around space-related topics pointed out a pattern. They traced the history of how NASA handles potentially controversial imagery. Whether you believe such claims or not, they established a precedent for what some call scrubbing, the systematic removal or withholding of potentially controversial elements from space imagery before public release. In the early days of Mars exploration, orbiters provided feeds that radio enthusiasts could receive. When anomalies appeared in those feeds, word spread quickly. NASA's solution was to eliminate live feeds and switch to delayed release with processing time built in. The International Space Station occasionally broadcasts live video of Earth from external cameras. Multiple times over years, viewers have reported seeing objects in those feeds that seem unusual. Strange lights, structured shapes moving in unexpected patterns. Whenever such objects appear, the feed often cuts to a colored screen or switches to a different camera angle. NASA typically attributes interruptions to signal loss or routine camera switching, but timing often coincides suspiciously with whatever anomaly viewers were watching. Mars missions followed similar evolution. Early missions released imagery quickly, often within hours. But as public interest grew and image analysis tools became more sophisticated, NASA implemented more layers of review. Images now go through calibration processes, artifact removal, quality checks, and explanatory review before public release. This serves legitimate scientific purposes. Raw spacecraft data can be noisy, can contain instrumental glitches, can be misinterpreted without proper context. But it also creates a buffer period during which problematic imagery can be identified and handled differently. Some propose that the current situation with 3I/Atlas fits this pattern. 7 spacecraft photographed the object. At least some must have captured clear, detailed images. The absence of those images in public record, even as automated feeds continue from other instruments, suggests someone made a decision about what to release and what to withhold. Consider the sequence of events. October 1st, government shutdown begins. October 3rd, 3I/Atlas passes closest to Mars. October 7th, European Space Agency releases fuzzy images. October 8th, 9th, 10th, 11th, 12th, NASA remains silent. No processed images. No technical reports. No scientific papers analyzing Mars flyby data. Radio silence. Avi Loeb commented on the situation during an interview. He addressed whether the government shutdown represented some kind of conspiracy to hide information. His response was characteristically measured. The delay, he said, is not the signature of extraterrestrial intelligence. It's more a signature of terrestrial bureaucracy. He acknowledged the frustration but attributed silence to dysfunction rather than deliberate concealment. Perhaps that's accurate. Perhaps silence really does come down to furloughed employees and stalled workflows. But the timing remains remarkable. After months of anticipation, after perfect positioning of multiple spacecraft, after the astronomical community marked October 3rd as the date when definitive answers would arrive, the curtain came down at the exact moment the show was supposed to start. October 29th, 2025 approaches. This date carries significance because it marks perihelion, the point where 3I/Atlas reaches its closest distance to the Sun. For observers on Earth, this creates a geometric problem. The visitor will be positioned almost directly behind the Sun from our perspective, hidden in solar glare, completely unobservable from ground-based telescopes. This blackout period extends from late October through most of November. Earth-based astronomers lose visual contact with the interstellar visitor precisely when it should be at its most active. Solar heating intensifies dramatically as objects approach perihelion. Comets typically display peak outgassing during this phase, their ices vaporizing rapidly under intense radiation. If 3I/Atlas truly is a natural comet, perihelion should trigger spectacular activity. Bright jets of gas and dust, potentially even fragmentation if thermal stress exceeds structural integrity. But we won't be able to watch it happen from Earth. The Sun blocks our view completely. This isn't unusual. Comets pass behind the Sun regularly, and astronomers simply wait for them to emerge on the other side. What makes this situation different is the constellation of questions already surrounding 3I/Atlas. The anomalous chemistry, the unusual trajectory, the missing Mars flyby images. All of it compounds into a scenario where the object disappears from observation at the most critical moment. If 3I/Atlas is a natural comet, perihelion might cause it to break apart. Thermal stress and tidal forces from the Sun's gravity can tear fragile icy bodies into pieces. Other comets have disintegrated when approaching the Sun, unable to withstand the heating. Jets of vaporizing gas can also spin up a comet's rotation. If outgassing isn't distributed evenly across the surface, it creates torque, acting like tiny thrusters that accelerate the nucleus. Fast rotation introduces centrifugal forces that can tear weakly bound material apart. If 3I/Atlas fragments at perihelion, Earth-based observers will see multiple pieces emerge in early December instead of one coherent object. But there's an alternative scenario. If 3I/Atlas is technological, if the object is a spacecraft rather than a natural comet, perihelion provides a unique opportunity. Hidden behind the Sun from Earth's perspective, the object could maneuver without being observed. It could use solar gravity to perform a gravitational assist, altering its trajectory in ways impossible for a passive rock. It could release smaller craft, mini-probes that separate from the main body and take up different orbits. The trajectory becomes significant here. 3I/Atlas moves opposite the direction planets orbit around the Sun. From the object's reference frame, planets are approaching it rather than receding. This geometry makes intercept calculations simpler. A probe released with velocity partly opposed to the main body's motion could slow down relative to the Sun, dropping into a bound orbit rather than continuing on an escape trajectory. Those probes could then wait, positioned along orbital paths where they would eventually encounter Earth, Venus, or Mars as those planets continue their circuits. Think of it like dropping breadcrumbs along a hiking trail. You don't need to aim each crumb at a specific target. You just place them along the path you know hikers will follow. The orbit of 3I/Atlas means released probes would naturally intersect planetary orbits simply by reducing their velocity relative to the Sun. This scenario assumes intent, assumes technology, assumes a level of capability that strains credulity for most scientists. But when dealing with unprecedented observations and unexplained anomalies, exploring low-probability possibilities remains scientifically valid when they stay consistent with available data. Let me take you back to an important question. Where did 3I/Atlas come from? Not in the immediate sense of its trajectory through our solar system, but in the deeper sense of which star system originally birthed this object billions of years ago. Researchers at Oxford University tackled this problem using sophisticated simulations. They input the visitor's observed velocity and position, then ran the trajectory backward through time, tracking which stars it might have passed near during its journey. When 3I/Atlas arrived in our solar system, it was moving away from the galactic center at 51 kilometers per second relative to the Sun. It was also moving upward through the galactic plane at 18.5 kilometers per second. That vertical component is unusually high. Most nearby stars and objects in the solar neighborhood have lower vertical velocities. This suggests 3I/Atlas belongs to what astronomers call the thick disk population rather than the thin disk. The Milky Way's disk actually has two components. The thin disk contains younger, metal-rich stars orbiting in a relatively flat plane. The thick disk contains older, metal-poor stars formed when the galaxy was younger, orbiting in a more vertically extended distribution. If 3I/Atlas came from the thick disk, it's likely ancient. Researchers estimated its age between 7.6 and 14 billion years old. The Sun, for reference, is 4.6 billion years old. This visitor could predate our entire solar system by billions of years. It might have formed when the universe was less than half its current age, making it a relic from an earlier epoch of galactic history. Think about that for a moment. If this object is 10 billion years old, it formed when the universe looked fundamentally different. The Milky Way was younger, more chaotic, with active star formation throughout. An object that old has witnessed the evolution of the galaxy. It's been traveling through space longer than Earth has existed. Our entire solar system, our planet, all of life's history on Earth, everything we know and care about, all of it occurred while 3I/Atlas was already ancient, already wandering between the stars. Researchers attempted to trace it backward through the galaxy to identify possible parent stars. They used data covering over 13 million stars, running simulations to determine which 3I/Atlas might have passed within close range during the past 10 million years. The simulations identified 93 potential encounters. But here's the problem. None of those encounters produced meaningful trajectory changes. The conclusion? No stellar flyby within the past 10 million years can account for the current trajectory. The visitor wasn't recently ejected from any nearby star system. It's been traveling through interstellar space for much longer, potentially hundreds of millions or even billions of years. This creates a fascinating picture. 3I/Atlas is a wanderer in the truest sense. It formed around some unknown star billions of years ago. Gravitational interactions, probably with a giant planet or close stellar encounter, kicked it out of its birth system. Since then, it's been drifting through the galaxy, occasionally passing through star systems like ours, but mostly traveling through vast, empty spaces between stars. During that journey, cosmic rays have bombarded its surface. Interstellar dust grains have sandblasted it. Ultraviolet light from distant stars has processed its surface chemistry. All these effects alter the object's properties over time, changing composition in ways that might mask its original signature. Early December 2025 will mark a pivotal moment. After weeks hidden behind the sun, 3I/Atlas will emerge into observable positions for ground-based telescopes. The predicted brightness places it at the edge of what binoculars can detect under dark conditions. For clear confirmation, you need a telescope. 8 inches of aperture provides comfortable margin. What observers see during those first nights will answer immediate questions. Is it intact? Does it appear as a single object or multiple fragments? Has brightness changed dramatically? Is there visible tail development? Does the trajectory match predictions or show deviations? These observations will come from dozens of locations simultaneously. Amateur astronomy clubs coordinate campaigns through online forums. Someone in Australia gets the first look as it rises above their eastern horizon. They post initial reports, brightness estimates, descriptions. Hours later, observers in the Middle East pick up the watch, then Europe, then the Americas. The relay continues, building a continuous observational record spanning days and weeks. Professional observatories will join the effort. Survey telescopes will measure precise positions for analysis. Spectroscopic facilities will analyze chemical composition, checking whether perihelion altered the outgassing mix. Monitors will track brightness variations that might indicate rotation or outburst activity. If 3I/Atlas fragmented during perihelion, first observations will reveal multiple objects where one used to be. Each fragment will have its own slightly different trajectory based on separation velocity and direction during breakup. Tracking those fragments over subsequent nights will allow reconstruction of when and how breakup occurred. Natural fragmentation typically produces pieces that drift apart slowly, meters per second relative velocity. Fragments stay relatively close together for weeks before gradually separating into distinct orbits. But suppose observations show something different. Suppose multiple objects appear, but their separation velocities are higher than natural fragmentation would produce. Or suppose objects display accelerations that can't be explained by outgassing. That would demand explanation. This scenario remains speculative. No current evidence suggests fragmentation will occur at all. Many comets survive perihelion intact. Thermal stress will be significant, but probably not catastrophic. The object should emerge intact unless its internal structure is unusually weak or unless something other than natural behavior is occurring. The trajectory question becomes critical during December observations. Orbital predictions based on pre-perihelion data assume only gravitational forces. But comets experience forces from outgassing. When jets of gas escape the nucleus, they create thrust, changing velocity slightly. These changes accumulate over time. Astronomers account for this by adding acceleration terms to orbital models, treating outgassing thrust as unknowns to be solved for along with orbital elements. If fitted parameters are consistent with observed outgassing, if thrust amount matches measured gas production rates, then natural processes explain the trajectory. But if deviations exceed what observed outgassing should produce, you have a problem. Either measurements are incomplete missing some component of activity, or some other force is acting on the object. December observations will provide the first test of whether post-perihelion trajectory matches predictions. Data will accumulate night by night. After a week, preliminary fits will narrow uncertainties. After 2 weeks, constraints tighten further. By end of December, astronomers will have a solid handle on where it's going and whether its path deviates from expectations. If deviations appear, the scientific community will debate significance. Small deviations within the range explainable by outgassing will generate papers, but won't trigger major controversy. Large deviations, changes inconsistent with natural behavior, will trigger intense scrutiny. Meanwhile, the JUICE spacecraft will be conducting observations between November 2nd and 25th. Those observations overlap with the period when the visitor is still behind the Sun from Earth's perspective. JUICE will see it during and immediately after perihelion, capturing data about its most active phase. But that data won't reach Earth until February 2026. This creates a strange information gap. December observers will see the aftermath without knowing exactly what happened. They'll see whatever state post-perihelion, but won't have detailed observational record of the perihelion passage itself. The JUICE data, when it finally arrives, will fill that gap retroactively, but for intervening months, interpretation will rely on inference rather than direct observation. Suppose December observations show the visitor intact and on trajectory consistent with natural outgassing. That would support the conventional hypothesis. The unusual pre-perihelion chemistry and other anomalies would remain interesting but explicable within natural frameworks. The story would likely fade from public attention as it becomes just another interstellar visitor. Unusual but not revolutionary. Alternatively, suppose December observations reveal something unexpected. Multiple objects with separation characteristics inconsistent with natural fragmentation, or trajectory deviations exceeding plausible outgassing effects, or spectroscopic signatures that don't match any known composition. Any of these would reignite debate and demand explanation. While scientists debate methodology and evidence standards, a parallel conversation exploded across social media. 3i/Atlas became a trending topic with thousands of posts analyzing images, sharing speculation, spreading misinformation. The pattern follows a familiar trajectory for astronomical phenomena that capture public imagination. Initial excitement spreads through early adopters. Then mainstream attention kicks in as news outlets cover the story. From there, narrative fragments into countless variations as different voices add interpretations, corrections, embellishments, and fabrications. Some discussion remained grounded in actual observations and scientific analysis. Amateur astronomers shared telescope images, compared notes on visibility, discussed processing techniques. Science communicators tried to provide accurate context, explaining what it is, where it came from, why it's interesting. But other content veered into speculation unconstrained by evidence. Some posts claimed it was definitely an alien mothership. Others warned it posed imminent threat despite trajectory staying far beyond Mars orbit. Conspiracy theories proliferated. A particularly viral post falsely attributed statements to a prominent physicist, claiming he said the visitor was accelerating toward Earth with possible hostile intent. The post included a manipulated screenshot from a television interview with text overlaid suggesting dramatic claims. The image spread rapidly, accumulating hundreds of thousands of views before fact-checkers identified it as fabricated. But by the time fact-checks appeared, false claims had already spread through networks of users who wanted to believe the dramatic narrative. This illustrates a fundamental challenge in modern information environments. Truth and fiction spread at different rates through different pathways. Accurate but mundane information generates modest engagement. Sensational but false information generates massive engagement because it triggers emotional responses. Platform algorithms optimize for engagement. Posts that generate clicks, shares, comments get amplified. This creates selection pressure favoring content that provokes strong reactions regardless of accuracy. Scientists carefully hedging statements with appropriate uncertainty get drowned out by confident voices making definitive claims. The visitor became a canvas onto which people projected existing beliefs. Those already convinced governments hide evidence of extraterrestrial contact saw NASA's silence as confirmation. Those skeptical of institutional authority interpreted missing images as intentional concealment. Those interested in apocalyptic scenarios transformed it into a threat despite trajectory, keeping it millions of kilometers from Earth. One persistent narrative claimed military forces were preparing to deflect or destroy it. Posts referenced alleged mobilizations, secret meetings, coordination between defense agencies. These claims lacked any factual basis, but the narrative persisted because it fit a particular worldview. Other social media users took a different approach, treating the visitor as entertainment rather than genuine mystery. Memes proliferated. Humorous takes acknowledge speculation while maintaining ironic distance. This entertainment framing serves a social function. It allows people to engage without committing to specific beliefs. But humor and misinformation exist on a continuum. What starts as obvious satire can get taken literally by audiences who don't recognize the joke. For researchers studying the visitor, this social media storm creates additional complications. When trying to communicate scientific findings to the public, you're competing with a flood of other voices, some helpful, many not. Let's step back from technical details and consider the broader pattern this visitor exemplifies. This isn't the first time an astronomical discovery has triggered speculation about non-natural origins. Understanding why requires examining how we process unusual observations and what happens when institutions control access to information the public desperately wants. Oumuamua established the template. When astronomers detected the first confirmed interstellar object in October 2017, its unusual properties immediately sparked debate. The elongated shape, the acceleration as it left the solar system, the lack of visible outgassing despite that acceleration, all seemed strange. Some proposed it might be a light sail, a thin reflective structure pushed by solar radiation. Most astronomers favored natural explanations. The controversy played out in journals, in media, across social media. Some scientists expressed frustration with the extraterrestrial hypothesis, arguing it was premature and unsupported. Others defended the value of considering all possibilities when dealing with unprecedented observations. The debate revealed philosophical differences about how science should handle ambiguous evidence for extraordinary claims. Borisov discovered in August 2019 provided contrast. It looked and behaved like a comet from moment of detection. Clear activity, obvious tail, signatures matching known compositions, trajectory changes consistent with outgassing. Nobody proposed alien origins because nothing about it demanded exotic explanation. It represented what astronomers expected based on understanding of how solar systems form and eject material. 3I/Atlas lands somewhere between these extremes. It shows activity unlike Oumuamua, but it also displays unusual properties distinguishing it from typical comets like Borisov. Whether those unusual properties require exotic explanations or just reflect natural variation remains the core question. But beyond specific scientific debates, this visitor illustrates something about information control and public trust. When NASA's orbiters were positioned to capture detailed images, when timing was perfect for answering key questions, the government shut down. Maybe timing was genuinely coincidental. Maybe bureaucratic dysfunction rather than deliberate concealment explains missing images. But optics are terrible. People naturally assume agencies that routinely manage complex space missions can handle image release during shutdowns if they want to. The perception, whether accurate or not, is that someone made a choice about what to release and what to withhold. This connects to longer history of government secrecy around space-related observations. When the Pentagon released UAP videos in 2020 confirming military pilots had encountered aerial phenomena defying easy explanation, it validated claims researchers had been making for decades. The government really was tracking unexplained objects. They really did have footage they hadn't released. Those who said we're not being told everything we're in that specific case correct. This doesn't mean every theory is true. Most aren't. But it means institutional credibility suffers when agencies that previously dismissed topics later admit they were taking those topics seriously all along. 3i/Atlas sits within this complex landscape of trust, transparency, and speculation. Maybe it's just a comet. Maybe anomalies are artifacts of incomplete observations and will disappear as more data accumulates. Maybe missing images will eventually be released showing completely ordinary features. Or maybe something stranger is happening either with the object itself or with how information about it is being managed. Without access to full data, the public can't evaluate these questions independently. They're dependent on institutional gatekeepers to release information, provide context, explain what they're seeing. When those institutions go silent at critical moments, people fill the vacuum with speculation. The challenge for scientists working within institutions is that transparency has limits. Some data requires careful calibration before release because raw observations can be misleading. Some information is restricted by agreements about satellite capabilities. Some results need peer review before public announcement to avoid spreading premature conclusions. All of these are legitimate reasons for not immediately releasing everything. But from an outside perspective, those justifications look like excuses. When excitement builds around a discovery, when public interest peaks, when everyone wants to know what's happening, being told you have to wait months for data processing feels like stonewalling. This tension won't be resolved by one object alone. It's structural, built into how modern science operates within institutional frameworks that have their own priorities, constraints, and risk tolerances. The scientific community values careful verification. The public values immediate transparency. Social media rewards speed over accuracy. Government agencies prioritize control over disclosure. These competing values clash repeatedly whenever controversial topics arise. What this visitor represents beyond its specific properties is a test case for how we handle unusual observations in an era of distributed information and institutional distrust. The traditional model where experts make pronouncements and the public accepts them has broken down. People want evidence, not just conclusions. They want to see data, run their own analyses, form their own judgments. Amateur astronomers downloading raw archives and processing them independently exemplify this shift. They're not content to wait for official releases. They're not willing to simply trust that experts will tell them everything important. Science has adapted to previous cultural shifts. When the printing press enabled wider distribution of knowledge, when public education expanded literacy, when universities opened enrollment beyond wealthy elites, the scientific community adapted its communication methods. The current transition to social media and distributed information networks requires similar adaptation. Scientists need to figure out how to maintain rigor and accuracy while operating in environments that reward speed and engagement. 3i/Atlas will eventually leave the solar system. By late 2026 or early 2027, it will have crossed Neptune's orbit and headed back into interstellar space. Observations will end. The object will fade into distance, too far and too faint for our telescopes to track. Whatever we learn, we'll learn before it disappears. After that, it becomes another entry in databases, another reference point for future researchers. But the questions it raises will persist. Questions about how we evaluate unusual observations. Questions about what evidence justifies exotic hypotheses. Questions about institutional transparency and public access to data. Questions about how science operates in the modern information landscape. If it turns out to be just a comet, it will have served a valuable purpose anyway. It forced these conversations. It revealed gaps in our observational capabilities, limitations of data release systems, challenges of communicating uncertainty to public audiences. Those lessons apply beyond this one object. And if it turns out to be something more than a comet, if December observations or JUICE data reveal properties that can't be explained naturally, then conversations become even more important. How humanity responds to confirmed evidence of extraterrestrial technology will depend partly on trust relationships between institutions and the public. We're approaching the moments when these questions get tested. Perihelion has passed or is passing. The object is behind the sun doing whatever it does when nobody's watching. Soon it will emerge. Telescopes will point. Images will accumulate. Data will flow. Answers, or at least better constrained questions, will arrive. Whatever happens, 3I/Atlas has already earned its place in astronomical history. The third interstellar visitor arriving at a moment when our detection capabilities were just mature enough to spot it. Strange enough to trigger serious scientific debate. Mysterious enough to capture public imagination. It came from the depths of space, carrying questions we're still learning how to ask, let alone answer. This ancient wanderer, billions of years old, has witnessed the evolution of our galaxy. It has traveled through the darkness between stars longer than Earth has existed. And now, for this brief moment in cosmic time, our paths intersect. We watch together as this visitor passes through our temporary home. This brief intersection of trajectories in the darkness between stars. The waiting continues. The observations approach. Night by night across telescopes scattered around our small planet, the story unfolds. All of us watching, wondering, questioning what secrets this mysterious traveler might reveal. Now, if you've made it this far, you're exactly the kind of person this channel needs. You understand that the biggest mysteries aren't always the loudest stories. They're the ones that require patience, curiosity, and willingness to question what we're told. So here's what I need you to do. First, leave a comment right now telling me what you think is really happening with 3I/Atlas. Do you think it's just an unusual comet, or is there something more to this story? Type natural comet if you think it's ordinary, or something else if you think there's more to discover. I read every comment, and your input helps shape future content. Second, smash that like button if you found this story fascinating. Likes tell the algorithm that this content matters, that people want deeper, more thoughtful explorations of mysterious phenomena. Third, make sure you're subscribed with notifications turned on. The next few months will be critical as observations continue, and you won't want to miss updates as this story develops. Finally, share this video with someone who loves mysteries, science, or just fascinating stories about our universe. The more people who understand what's happening, the more pressure there is for transparency and answers. Thank you for spending this time with me, diving deep into one of the most intriguing astronomical discoveries of our time. The next video is already appearing on your screen, another story that will challenge what you think you know. I'll see you there. Keep questioning. Keep curious. Keep watching the skies. Let me pull you deeper into the layers of this mystery. Because what I've told you so far is just the surface. The trajectory anomalies, the chemical oddities, the missing images, these are the obvious questions. But underneath runs a current of implications that reaches far beyond one interstellar visitor. We're talking about how humanity responds when confronted with something that doesn't fit our models. How institutions manage information. How we decide what's possible and what isn't. Scientists analyzing 3I/Atlas discovered something else peculiar. The Swift Observatory, a NASA space telescope designed to detect gamma-ray bursts, turned its instruments toward the visitor in July and August. Swift detected hydroxyl emissions, the fingerprint of water molecules being broken apart by sunlight. But here's what caught researchers off guard. The comet was producing these emissions at 2.9 astronomical units from the Sun, nearly 3 times Earth's distance. That's way too far for water ice to normally sublimate directly from a comet's surface. The Sun isn't strong enough at that distance to heat ice past its vaporization point. Yet, 3I/Atlas was losing water at approximately 40 kilograms per second. That's equivalent to a fire hose running at full blast, continuously, from nearly 3 times Earth's distance from the Sun. For comparison, typical solar system comets start showing significant water activity around 1.5 to 2 astronomical units. They need that close proximity for solar heating to sublimate surface ice. So what's happening with 3I/Atlas? One explanation proposed by researchers involves icy debris clouds. Perhaps chunks of ice are floating in the cloud of gas and dust surrounding the nucleus. When sunlight hits these ice chunks, they act like miniature steam vents, releasing water vapor even though the main body remains too cold for direct surface sublimation. But this raises another question. Where are these ice chunks coming from? Are they being continuously ejected from the nucleus? If so, what mechanism is driving that ejection at such distances where solar heating should be minimal? Or did some fragmenting event earlier in the visitor's approach create a debris field that's only now becoming visible as it warms? The hydroxyl detection revealed something else interesting. Researchers calculated that at least 8% of the comet's surface must be active to produce the observed water loss rate. 8%. Most solar system comets show active regions covering 3 to 5% of their surface. The interstellar visitor displays roughly double the typical activity level. Every data point accumulated through summer and fall 2025 added another piece to a puzzle that refused to resolve into a clear picture. Some pieces fit natural comet models. Others didn't. The question scientists wrestled with wasn't whether the visitor was unusual. Everyone agreed it was unusual. The question was whether that unusualness represented extreme natural variation or indicated something fundamentally different. Avi Loeb pointed out in multiple interviews and blog posts that the visitor's properties placed it in a category he calls scientifically interesting objects. These are things anomalous enough to warrant serious investigation, but not so clearly artificial that they force immediate conclusions. The challenge with scientifically interesting objects is determining when you have enough evidence to favor exotic explanations over natural ones. Science operates on what philosophers call parsimony or Occam's razor. When multiple explanations fit the data, favor the simplest one requiring fewest assumptions. Natural comets exist. We've observed thousands. We understand their basic physics even if details vary. Alien spacecraft, as far as confirmed evidence goes, don't exist in our catalog of verified phenomena. So when faced with unusual comet, the parsimonious explanation defaults to natural unusual comet, not artificial craft. But parsimony has limits. If anomalies accumulate to the point where the natural explanation requires increasingly complex assumptions and ad hoc modifications, while the artificial explanation becomes comparatively simpler, the calculation shifts. Imagine trying to explain a Boeing 747 using only natural meteorological phenomena. You could construct elaborate stories about unusual wind patterns, atmospheric pressure variations, temperature gradients, all conspiring to create a metallic bird-shaped cloud that happens to carry smaller human-shaped clouds inside it. But at some point, the natural explanation becomes so contrived that the artificial explanation, humans built a flying machine, becomes simpler despite requiring acceptance of technological capability. The question with 3I/Atlas is where on that spectrum it falls. Are the anomalies explainable with modest extensions of natural comet models? Or do they require such extensive modifications that alternative explanations deserve consideration? Different scientists draw that line in different places based on their prior assumptions about how likely artificial objects are to exist in the first place. If you think technological civilizations are common in the galaxy and regularly send probes exploring other star systems, your threshold for considering artificial explanations drops. You're willing to entertain that hypothesis with less evidence because your prior probability is higher. If you think technological civilizations are rare or non-existent, your threshold rises dramatically. You'll exhaust every conceivable natural explanation before considering artificial ones, because your prior says artificial objects are vanishingly unlikely. This creates what researchers call confirmation bias. People tend to interpret ambiguous evidence in ways that confirm their existing beliefs. Those convinced governments hide evidence of extraterrestrial contact see the missing Mars orbiter images as confirmation. Those skeptical of such claims see bureaucratic dysfunction. Both groups have access to the same facts, but different frameworks for interpreting those facts. The visitor became a Rorschach test. Scientists see whatever their prior assumptions prime them to see. And here's the uncomfortable truth. Both groups might be partly right and partly wrong. Maybe it is a natural comet with unusual but explicable properties, and maybe institutional response has been clumsy but not conspiratorial. Or maybe properties are stranger than natural variation allows, and maybe institutions are being more cautious with information released than transparency advocates would prefer. The binary framing, either natural or artificial, either transparent or conspiratorial, might itself be the problem. Reality often occupies middle ground that resists simple categorization. Let's talk about what happens next. Because the story doesn't end with perihelion. It enters a new phase. As December 2025 approaches, ground-based observatories will begin recovering the visitor as it emerges from solar glare. Those first observations will be crucial. Astronomers will measure its brightness to see if it changed dramatically during the unobserved period. They'll analyze its trajectory to check for deviations from predictions. They'll examine its spectroscopic signature to determine if composition altered. Multiple research groups will publish papers analyzing the December data. Those papers will go through peer review, a process where other scientists evaluate methodology and conclusions before publication. Peer review serves as quality control, filtering out obvious errors and unsupported claims. But it's not perfect. Reviewers have their own biases. Journals have editorial preferences. Controversial papers face higher scrutiny than conventional ones. Getting a paper arguing for artificial origins published in a major astronomy journal would require extraordinary evidence, surviving extraordinary scrutiny. Papers arguing for natural explanations face lower bars because they align with dominant paradigms. This creates a publication bias. Conventional interpretations get published and cited more easily than unconventional ones, creating feedback loops where conventional wisdom becomes further entrenched regardless of whether it's actually correct. Scientists who propose unconventional ideas risk professional reputation. Tenure committees, grant agencies, colleagues, they all evaluate researchers partly based on whether their work aligns with accepted frameworks. Step too far outside those frameworks, and you risk being labeled a crank, losing funding, damaging career prospects. This pressure toward conformity serves useful purposes. It prevents science from fragmenting into competing schools of thought that can't communicate. It maintains standards and rigor, but it also stifles innovation when genuinely new phenomena appear that don't fit existing categories. Some of history's most important scientific breakthroughs initially faced rejection precisely because they challenged dominant paradigms. Continental drift, the theory that Earth's continents move over geological time, was ridiculed for decades before plate tectonics provided the mechanism explaining how it worked. The existence of meteorites, rocks falling from space, was dismissed by the French Academy of Sciences in the late 1700s despite eyewitness accounts. The Academy couldn't imagine a mechanism for rocks to be in space, so they rejected the observations as unreliable. Later, Of course, meteorites became accepted as scientists developed better understanding of the solar system. The visitor might represent a similar situation, if its properties genuinely indicate something beyond natural comets. The scientific establishment will need time to process that. Initial papers will likely favor conservative interpretations. Only gradually, as evidence accumulates and conventional explanations fail to account for observations, might consensus shift, or evidence might ultimately support natural explanations decisively, resolving anomalies within extended but conventional frameworks. We won't know until data arrives and analysis proceeds. Meanwhile, the public conversation will continue on social media, in comments sections, across forums and chat groups. People will debate what they think is happening based on whatever information is available, filtered through their various biases and beliefs. Some will advocate for patience, trusting that scientific process will eventually yield answers. Others will demand immediate transparency, suspicious of institutional gatekeeping. The tension between these positions reflects deeper disagreements about authority, expertise, and who gets to decide what counts as legitimate knowledge. In democratic societies, we've generally agreed that scientific expertise should guide technical questions. We trust engineers to build bridges, doctors to treat diseases, physicists to explain fundamental forces. We do this not because experts are never wrong. They certainly are sometimes, but because systematic methods of investigation tend to produce more reliable knowledge than intuition or speculation. But that trust has eroded over recent decades. Partly this reflects real instances of experts being wrong or institutions betraying public trust. Partly it reflects coordinated campaigns by interests who benefit from undermining expertise in specific domains. And partly it reflects the democratization of information through the internet, which lets anyone with a connection challenge expert claims regardless of whether they have relevant training. The visitor arrives into this complicated landscape, a genuinely ambiguous phenomenon that experts are still figuring out, happening in real time as public watches and demands answers faster than careful analysis can provide them. It's a case study in how modern science communication works and doesn't work. Let me take you through some of the specific claims that have circulated about the visitor and examine which have evidence and which are speculation or misinformation. Claim 1. The visitor is accelerating in ways inconsistent with natural forces. Status: unverified. Some early observations suggested possible non-gravitational accelerations, but these were within margins explicable by outgassing. No definitive measurements have shown accelerations exceeding what outgassing could produce. This remains an open question pending more observations. Claim 2. NASA deliberately suppressed high-resolution images from Mars orbiters. Status: unclear. The government shutdown coincided with the Mars flyby, creating plausible explanation for delayed releases. However, no high-resolution images have been officially released even after the shutdown ended. Whether this represents deliberate suppression, ongoing processing delays, or image quality issues remains unknown. Claim 3. The visitor's chemical composition differs fundamentally from solar system comets. Status: partially verified. The high carbon dioxide to water ratio is unusual but not unprecedented. One solar system comet shows similar composition. Whether this represents natural variation or indicates different formation environment remains debated. Claim 4. The visitor's trajectory was deliberately aimed at our solar system. Status: highly speculative. The low inclination relative to the ecliptic plane is statistically unusual but not impossible for random interstellar objects. The 5 in 100,000 probability cited by Loeb assumes uniform distribution of interstellar object trajectories, which may not be accurate. Natural selection effects could bias detected objects toward lower inclinations without requiring deliberate targeting. Claim 5. The visitor will release probes at perihelion. Status: pure speculation. No evidence supports this. The idea comes from hypothetical scenarios about what advanced civilizations might do, not from actual observations. Claim 6. Military forces are preparing to engage the visitor. Status: false. No credible evidence supports military engagement. The visitor's trajectory keeps it far from Earth, posing no collision threat. This claim appears to be fabricated misinformation. Claim 7. The visitor might be billions of years old. Status: plausible but uncertain. Trajectory analysis suggests it likely comes from the thick disk population of the galaxy, which formed billions of years ago. But tracing its origin precisely is impossible without knowing its exact birthplace. Understanding which claims have evidentiary support and which are speculation helps navigate the information landscape more effectively. Not everything you read about the visitor is equally reliable. Some sources cite actual scientific papers and telescope observations. Others cite unnamed insiders, vague government sources, or pure speculation dressed up as fact. Developing skill at distinguishing these requires practice and skepticism, but it's increasingly essential in environments where misinformation spreads as easily as accurate information. Here's something fascinating I haven't mentioned yet. Research teams studying the visitor discovered that its dust production rate is relatively low despite the high water production. It's losing significant amounts of water, but not proportionally high amounts of dust. This imbalance suggests the nucleus might be depleted in dust, having lost most of its dusty component during earlier passes through other star systems or during its ejection from its birth system. If confirmed, this would indicate the visitor is old and weathered, having undergone significant evolution since its formation. Another intriguing detail comes from color measurements. The visitor appears slightly reddish in optical observations, with spectral slope indicating reddening consistent with organic compounds on the surface. Similar colors appear on some outer solar system objects like Kuiper belt bodies, where organic chemistry has processed surface ices over billions of years. The color suggests the visitor has spent long periods exposed to cosmic radiation and interstellar medium, gradually building up complex organic molecules through chemical reactions. This organic-rich surface could have implications for astrobiology. If interstellar visitors regularly carry organic molecules between star systems, they could potentially spread the chemical building blocks of life throughout the galaxy. This doesn't mean the visitor carries life itself, but it might carry the ingredients that could contribute to life's emergence on suitable worlds. The concept is called panspermia, the idea that life's building blocks or even simple organisms might spread through space via comets, asteroids, and dust grains. It's been discussed for over a century, but remains controversial because we lack definitive evidence either supporting or refuting it. The visitor provides a test case. If it carries organic molecules formed in another star system, that would demonstrate chemistry necessary for life isn't unique to Earth's neighborhood. It would suggest the molecular precursors of life are widespread in the galaxy, increasing the probability that life itself is common. Researchers using radio telescopes also attempted detecting any radio emissions from the visitor that might indicate technological activity. The Breakthrough Listen project, which searches for signs of extraterrestrial intelligence, pointed instruments toward the visitor multiple times during summer and fall 2025. They scanned across billions of radio frequency channels looking for narrowband signals or patterns that might suggest artificial transmission. Results? Nothing. No radio signals detected above background noise. This doesn't definitively rule out technological origin because a probe might not be transmitting radio waves, or might transmit in frequencies or patterns the search didn't cover. But it does constrain possibilities. Any sufficiently powerful radio transmitter on or near the visitor would have been detected. The non-detection means if it's technological, it's either not transmitting in radio frequencies or transmitting at power levels below detection thresholds. Breakthrough Listen also searched for optical laser pulses, brief flashes of light that might represent optical communication attempts. Again, nothing detected. These null results don't resolve the question of the visitor's nature, but they inform probability assessments. An artificial probe actively trying to communicate with or study planetary systems would likely emit some kind of detectable signal. The silence suggests either it's natural, or if artificial, it's passive rather than actively broadcasting. Let's zoom out to the bigger picture for a moment. Why does this visitor matter beyond its immediate scientific interest? What does it tell us about ourselves and our moment in history? We're living through a transition period in human civilization's relationship with space. For most of history, space was unreachable, observed only through naked eyes and later telescopes, but fundamentally separate from human activity. The 20th century changed that. We began sending spacecraft beyond Earth. We landed on the moon. We built space stations. We sent probes to every planet in our solar system and beyond. We've now reached a stage where we can detect objects from other star systems passing through our cosmic neighborhood. We can study them with multiple instruments across different wavelengths. We can track their trajectories and analyze their compositions. This capability is unprecedented in human history. Previous generations could only wonder about interstellar space. We can actually observe and study it. But we're still early in developing this capability. Our instruments have limitations. Our theoretical frameworks are incomplete. Our institutional structures for managing discoveries haven't fully adapted to the pace of new findings. The visitor exposes these growing pains. We have enough capability to detect and study it, but not quite enough to answer all the questions it raises. We have communication technologies that let global audiences follow discoveries in real time, but not effective frameworks for managing speculation and misinformation at that speed. We have scientific institutions with protocols for verifying and publishing results, but those protocols move slower than public demand for immediate answers. This gap between capability and completion, between what we can detect and what we can fully understand, creates the space where mystery and speculation thrive. And maybe that's not entirely bad. Mystery motivates exploration. The questions that remain unanswered after initial observations drive development of better instruments and more refined theories. The visitor will likely inspire a generation of astronomers and engineers to develop capabilities for studying the next interstellar visitor with greater sophistication. Already, plans are being discussed for dedicated observatories designed specifically to detect and track interstellar objects. Current detection is somewhat serendipitous. We spot these visitors when existing survey telescopes happen to catch them. But a purpose-built system could dramatically increase detection rates and provide earlier warning, allowing more thorough observation campaigns. The Legacy Survey of Space and Time, which will begin operating from the Vera Rubin Observatory in Chile, will dramatically increase the rate of interstellar object detection. The LSSD will scan the entire visible sky every few nights, capturing any moving objects. Researchers estimate it might detect dozens of interstellar visitors per year once fully operational. This will transform the field from studying rare anomalies to analyzing a population of objects, identifying patterns and statistics that single cases can't reveal. When we have data on 50 interstellar visitors instead of 3, we'll understand whether the visitor's unusual properties are genuinely anomalous or fall within a broader natural distribution. We'll see whether the flat trajectory is rare or common, whether the chemical composition is outlier or representative, whether the size estimates indicating large nucleus are accurate or result from observational artifacts. Population statistics will resolve many current ambiguities. But that data lies in the future. Right now, we're working with 3 known interstellar objects, each displaying different properties. Oumuamua showed little to no outgassing, but exhibited non-gravitational acceleration. Borisov appeared conventionally comet-like with clear activity and composition matching solar system comets. And now the visitor, showing high water production, unusual chemistry, and various other peculiarities. Sample size of 3 is too small for robust statistical conclusions. Every object looks unique when you only have 3 examples. It's like trying to understand human diversity by meeting 3 people. You'd note differences but couldn't determine which represent normal variation and which are genuine outliers. The visitor occupies this frustrating position where it's genuinely interesting, raising real scientific questions, but those questions can't be definitively answered without more data. This is actually normal in science. Progress often happens incrementally. First observation raises questions. Second observation adds information but doesn't fully answer them. Third observation provides more context. Eventually, accumulated data reaches a threshold where patterns become clear and theories can be definitively tested. We're in the early phase of that process for interstellar objects. Frustrating for those who want immediate answers, but typical for emerging fields of study. Here's something worth considering. Suppose the visitor turns out to be exactly what it appears to be, a natural comet from another star system displaying unusual but ultimately explicable properties. What would we learn? First, we'd learn that interstellar comets show greater diversity than we initially expected. The 3 confirmed visitors would have taught us that objects ejected from planetary systems elsewhere in the galaxy span a wide range of compositions, sizes, and behaviors. This would inform our understanding of planet formation processes throughout the galaxy, showing that conditions vary more than models based solely on our solar system suggested. Second, we develop refined techniques for studying fast-moving dim objects at large distances. The instruments and methods developed for observing the visitor would apply to future detection, improving our ability to characterize interstellar visitors. Third, we'd have tested various theories about interstellar object demographics, chemistry, and dynamics against real data. Even confirming that something is natural and ordinary advances knowledge by constraining possibilities and validating models. And fourth, we'd have gone through a societal learning experience about how to handle ambiguous discoveries that generate public excitement. The institutional responses, the communication challenges, the spread of speculation, all of these would inform future handling of similar situations. Now suppose instead that future observations reveal properties definitively inconsistent with natural origin. Suppose trajectory deviations can't be explained by outgassing. Suppose internal structure revealed through radio observations shows regular geometric patterns. Suppose spectroscopic analysis detects compounds that don't form naturally. What then? This would represent arguably the most significant discovery in human history. Confirmation that technological civilizations exist elsewhere in the galaxy and that their artifacts occasionally pass through our solar system would fundamentally transform our understanding of our place in the universe. It would raise immediate questions. Who built it? When? For what purpose? Is it still active? Are there others? Is the civilization that built it still around? How common are such civilizations? Why haven't we detected radio signals or other obvious signs of their existence? These questions would drive unprecedented scientific mobilization. Every major telescope would be redirected toward the visitor. International cooperation would intensify as nations recognized the global significance. Space agencies would fast-track missions to study it more closely, possibly even attempting rendezvous if trajectory allows. But it would also trigger social and philosophical disruption. Religions would grapple with implications for their cosmologies. Governments would debate security implications and whether protocols for international cooperation or competition should apply. Populations would experience psychological impacts as worldviews adjusted to confirmed existence of other intelligent life. The scale of impact would depend partly on what we learn. An ancient derelict probe from a long-extinct civilization would have different implications than an active craft from a still-thriving culture. A simple automated surveyor would raise different questions than a sophisticated vehicle displaying clear signs of advanced technology. Most impactful would be any indication of intent. A probe clearly designed to make contact with planetary civilizations would demand response. What message do we send back? Who decides what that message says? These aren't hypotheticals that can be casually dismissed. Multiple researchers and organizations have grappled with questions of how humanity should respond to confirmed detection of extraterrestrial intelligence. The SETI post-detection protocol outlines suggested steps for verification and announcement. The protocol emphasizes careful confirmation before public disclosure to avoid false alarms. It recommends international consultation before attempting any response transmission. And it advocates transparency in sharing information once detection is confirmed. But these are recommendations, not binding agreements. No global governance structure can enforce protocols if individual nations or organizations decide to act unilaterally. This is one reason some researchers argue for proactive development of international frameworks before a detection occurs, so coordination mechanisms are already in place if needed. The visitor, whether natural or artificial, has already served to highlight these gaps in our preparedness. If December observations or subsequent data reveal something truly anomalous, how quickly could international community mobilize effective response? Would cooperation prevail or competition? Would transparency win or secrecy? These questions don't have clear answers, which itself is revealing about current state of global coordination on potentially civilization-altering discoveries. Let me bring this back to you personally for a moment. Why should you care about an interstellar visitor that poses no threat to Earth and will exit our solar system regardless of what it is? Why does this matter beyond abstract scientific curiosity? Here's why. The visitor represents a test of human civilization's capacity to grapple with fundamental questions about reality. We're confronted with something that doesn't fit neatly into existing categories. Something that challenges assumptions about what's normal versus what's possible. How we respond, both individually and collectively, reveals what kind of species we're becoming. Do we approach mysteries with rigorous skepticism that demands evidence, but remains open to revising beliefs when data warrants? Or do we retreat into certainty, either dismissing anything unusual as easily explainable or accepting anything unusual as confirming pre-existing beliefs? The visitor tests whether we can maintain productive middle ground, taking anomalies seriously without jumping to unsupported conclusions. It tests whether institutions can balance legitimate needs for careful verification against public demands for transparency. It tests whether media can communicate scientific uncertainty accurately without either overhyping or underreporting significant findings. These tests matter because their practice runs for potentially more significant future scenarios. If we handle ambiguous discovery of an interstellar visitor poorly, mismanaging communication, allowing misinformation to dominate discourse, failing to maintain public trust in institutions, that bodes poorly for handling more consequential situations that might arise. But if we navigate this successfully, maintaining rigor while staying open to possibilities, communicating effectively despite uncertainty, building rather than eroding trust between institutions and public, that creates positive precedent and builds capability for whatever comes next. You're part of this test whether you realize it or not. Every time you engage with information about the visitor, every time you share a post, leave a comment, form an opinion, you're participating in this collective sense-making process. Your choices about which sources to trust, how critically to evaluate claims, how charitably to interpret ambiguous evidence. All of these micro-decisions aggregate into macro patterns that shape cultural response. So here's my challenge to you. Approach the visitor and future mysteries like it with radical intellectual honesty. Question your own assumptions as rigorously as you question official narratives. Demand evidence, but recognize that absence of evidence isn't always evidence of absence. Stay curious enough to consider possibilities that make you uncomfortable. Stay skeptical enough to reject claims that lack support. This balanced stance is difficult to maintain. It requires holding tension between opposing impulses rather than collapsing into comfortable certainty on either side. But it's the stance that best serves truth-seeking. It's the stance that honors both the empirical rigor of scientific method and the imaginative possibility of genuine discovery. We live in a remarkable moment. For the first time in human history, we can detect and study visitors from other star systems. We have instruments powerful enough to characterize these objects in detail. We have communication networks that let global audiences follow discoveries in real time. And we have growing awareness that the universe might hold surprises that challenge our deepest assumptions about reality. The visitor is one small piece of that larger story, but it's a piece that's happening now that you can follow and participate in understanding. The next few months will bring new observations. The data from JUICE will eventually arrive. Papers will be published. Debates will continue. And through it all, this ancient wanderer will continue its journey, caring nothing for our questions and theories, simply existing as whatever it is. Whether that's a natural comet weathered by billions of years in interstellar space or something stranger, we'll learn together as evidence accumulates. Before we close, I want to leave you with one final thought. The visitor, regardless of its nature, carries a message, not an intentional communication, but an inherent significance. It reminds us that our solar system isn't isolated. We're embedded in a galaxy containing hundreds of billions of stars, many with their own planetary systems. Objects ejected from those distant systems occasionally wander through our cosmic neighborhood. This will continue happening throughout our future. More visitors will arrive. Some will detect. Most will miss. Each one represents a messenger from another corner of the galaxy, carrying information about conditions, processes, and possibilities we can only glimpse indirectly. The visitor also reminds us how much we don't know. Despite centuries of astronomy and decades of space exploration, we're still surprised by relatively simple objects passing through our solar system. If a comet can puzzle us this thoroughly, imagine how much remains unknown about more complex phenomena. Humility in the face of cosmic mystery isn't weakness. It's realism. We're clever apes on one small planet, only recently developing tools to study the universe beyond our immediate surroundings. We've made remarkable progress, but we're nowhere near complete understanding. That realization should inspire rather than discourage. Every mystery solved reveals new questions. Every observation raises new puzzles. The process of discovery is infinite. There's always more to learn, always deeper levels of understanding to pursue. The visitor participates in that endless dance of question and answer, mystery and revelation. It arrived from the deep darkness between stars, briefly illuminated by our sun, observed by our instruments, contemplated by minds trying to understand. Soon it will return to that darkness, vanishing beyond our ability to observe. But the questions it raised will persist, driving future observations, inspiring new generations of researchers, expanding human knowledge one hard-won discovery at a time. So if you've made it all the way to the end of this deep exploration, you're exactly the kind of engaged, curious person who makes this community special. Now I need you to take action. Leave a comment right now telling me your honest assessment. Type natural if you think the visitor is an unusual but ordinary comet. Type unknown if you genuinely think the evidence remains too ambiguous to decide. Or type artificial if you think there's enough anomalies to seriously consider non-natural explanations. I read every single comment, and your input genuinely shapes the content we create here. Second, smash that like button if this deep dive satisfied your curiosity and made you think differently about this discovery. Likes tell the algorithm that substantive, thoughtful content deserves amplification over clickbait and sensationalism. Third, subscribe and hit the notification bell so you don't miss updates as this story develops. The next observations are coming soon, and you'll want to be among the first to know what they reveal. And finally, share this with someone who would appreciate this level of depth and analysis. The more people who understand the real complexities of this mystery instead of oversimplified narratives, the better our collective conversation becomes. Thank you for investing your time and attention in understanding one of the most intriguing astronomical stories of this decade. The next video is queued up on your screen. Another fascinating exploration of mysteries at the intersection of science and wonder. I'll see you there. Until then, keep looking up, keep questioning, and keep that sense of cosmic curiosity alive. Because out there in the darkness between stars, more visitors are traveling, more mysteries are waiting, and humanity's greatest discoveries still lie ahead of us. Clear skies and curious minds, everyone.